Okay, let me starting this last lecture recalling the high order averaging method for continuous differential equation. So differential equation given in this standard form, we have a power series of epsilon up to k, and all the coefficients, the functions here is assumed to be only continuous. Okay, we are not assuming, for instance, Lipschitz in the second variable. Here, all the functions are only continuous functions. And for this kind of differential equation, we defined the high order averaged functions hi just by taking the average of each coefficient of epsilon power to I. So hi is the average of fi, okay, the average in time. And we also assumed the hypothesis H that imposes for a given subset V such that the closure of V is contained in the domain. We assume that there exists an epsilon 1 such that for each lambda in the open interval 0, 1 and each epsilon between 0 and epsilon 1, any t-periodic solution of this difference equation is entirely contained in V. So note that the difference equation is defined in this domain, the closure of V. Then when I say a t-periodic solution of this difference equation, I am assuming that this is contained in the closure of V. So the hypothesis says that if this difference equation has a periodic solution, that means this difference equation has a periodic solution containing the closure of V, then it has to be entirely contained in the interior of V. In particular, if this difference equation does not have periodic solutions, then this hypothesis is automatically satisfied, okay? So, for this kind of difference equation, we have the usual statement for the higher order averaging method. Denote H0 equals 0 and let L be the index of the first order non-vanishing averaged function. Okay, so H0 up to HL minus 1 is equals 0 and HL is distant from 0. Then we assume that for a 0 of this averaged function, there exists a neighborhood V with the closure of V contained in D, satisfying three things. The first one, HL is distant from 0 for every Z in the closure of V minus Z star. That means that V is an isolating neighborhood for Z. We also assume that hypothesis H is satisfied for this V, okay? And that the Brouwer degree of HL V0 is distant from 0. Yes, is distant from 0. Then the result is that for the epsilon sufficiently small, the difference equation 10, this one, has a t-periodic solution contained in the closure of V for every time and converging uniformly to a constant function, Z star, as epsilon goes to 0. Okay, so this is the result. We discussed also some consequences that comes from the negation of hypothesis H. So when we have to check hypothesis H, we assume its negation, and we have this consequence. I'm not going to recall this now because it will appear in the application, and we will comment with more attention. And I also provide another property, a geometric property that's not equivalent to hypothesis H, but at least implies in hypothesis H. Okay, so just a comment. One could ask me, why we did not follow the same approach that we had before for instance, the continuous Lipschitz case. Okay, so recall that the approach in the Lipschitz case involves expanding the displacement map around epsilon equal to 0. And in order to define the displacement map, we need to define the time t map. Okay, and this time t map, in order to define this map, we need at least the uniqueness of solutions passing through a specific initial condition. And since we are only assuming the continuity of our differential equation, we do not have guaranteed such property. Okay, so we cannot define the displacement function in order to expand the displacement function in power series of epsilon. So that's why we need to work with this other approach, that is the operator equation approach, just to complement what we discussed in the last lecture. Okay, so let's start now this example, an example of a non-Lipschitz continuous perturbation of harmonic oscillation in light of our last theorem. Okay, so here we consider x double dot equal minus x plus a first order perturbation, epsilon times x squared plus x dot square, plus a k order perturbation. Okay, so a power to k that multiplies x squared and that multiplies times this function, which is a non-Lipschitz function. It's the cubic root of x squared plus x dot squared minus 1. So note that this function is not locally Lipschitz in any neighborhood of SE1 of this circle. Okay, because here we have the cubic root of this function. So it's not Lipschitz in any neighborhood of S1. And plus the remainder, higher order terms in epsilon. The result that we get applying the last theorem is that for any positive integer k and epsilon sufficiently small, this difference equation admits a periodic solution converging to SE1 uniformly as epsilon goes to 0. So when we have a difference equation which is eventually non-Lipschitz in a specific region, and we compute the average function, and we see that the 0 of this average function is located at some point that which the difference equation is Lipschitz in the neighborhood of this point, we would not have to use the private theorem, because we could try to restrict the domain of our difference equation and just use the classical averaging theorem. This happens, for instance, we will see in discontinuous piecewise difference equation that when you compute the average function, you see that its zeros are located in some place where the function is continuous, for instance, is smooth. Then you do not have to use any stronger version of the averaging theory in order to detect the limit cycles in this case. However, here we will see that the 0 of the average function that we will compute here is located exactly where it's not Lipschitz. Then we cannot restrict our initial difference equation in order to work in a domain where everything works well. So here we need the last theorem in order to study product solutions for this difference equation. Okay, let's continue. So in order to study this difference equation, it's a perturbation of a harmonic oscillator. We have discussed the system several times here. Then the first thing we have to do is the first step which consists in transforming this difference equation in the standard form for applying the averaging method. So we apply a polar change of coordinates, and we and we write the system in a system like this, where f theta r epsilon is equal this power series of epsilon. So here we have the sum for epsilon power to 0 until epsilon power to k minus 2. And here we have the term epsilon k epsilon power to k minus 1 times this function. So the non-Lipschitz part, this one, appears here in the transformed system. So here we have the cubic root of r squared minus 1. So for in any neighborhood of r equal 1, this function is not Lipschitz. Okay. So now what we have to do is compute the averaged functions, HIs. We see that when we integrate this function, okay, between 0 and 2 pi, because the period here is 2 pi, then this integral vanishes. So hi is equal to 0 for I between 1 and k minus 1. And when we compute the kth averaged function, since we have to integrate this function, this also vanishes, but here we have a sine square, and this does not vanish. And the average function of order k is given by this expression, r cubic root of r squared minus 1 divided by 2. So this is a non-Lipschitz function in a neighborhood of r equal 1. So here I'm drawing the graph of hk, and we see that hk has two zeros. The first one is r equals 0. It's not interesting for us because it's not in the domain. And the second zero is 1, and that is the point where the function becomes vertical. Okay, so the integral here goes to infinity, so it's not Lipschitz in a neighborhood of 1. So in order to check the hypothesis of our averaging theory in this context, the first thing we have to do is to compute the Brauer degree of this function in a neighborhood of its zeros. Okay. In order to do that, we can use the homotopy property of the Brauer degree. It's constant under some suitable assumptions during the deformation. Okay. So the idea here is to construct an homotopy between HR and the linear function R minus 1. That's the idea. So we can choose a nice domain here, for instance, 1 minus alpha and 1 plus alpha. This will be our V. Okay, and in this domain we can construct an homotopy between these two functions in order that during the deformation the unique zero of the function is 1. So we have ensured the hypothesis of the property, the invariance property of the Brauer degree, in order that the Brauer degree of this function coincides with the Brauer degree of this function. This function is linear differentiable, and we can compute its Brauer degree using the formula that I have provided in the last lecture. Okay, so we see that the Brauer degree is equal to 1 distinct from 0. Okay, so it only remains now to check hypothesis H for this differential system. Okay, so in order to check this hypothesis, we assume that it does not hold. So we assume the negation of hypothesis H. And as I have commented in the last lecture, its negation provides the numerical convergent sequences epsilon m and lambda n. Epsilon m belongs to this interval, which is open at 0, which is important, and lambda m is contained in this open interval, such that epsilon m goes to 0 and lambda m goes converges to some point in the now closed interval 0, 1. Okay. We also have a sequence of 2 pi periodic solutions of this differential equation. Okay, so Rm, the image of Rm is contained in the closure of V, and the derivative of Rm satisfies this differential equation, and for which there exists an instant belong to 0 to pi, such that Rm of this instant, theta m, belongs to the boundary of V. Okay, so that's the negation of hypothesis H. And as an application of the Arzelà-Askew theorem, we can see, notes that the derivative of this function goes to 0 as m goes to infinity, because we have this epsilon multiplying everything here. Then, by as an application of the Arzelà-Askew theorem, we can see that this function can be taken, by taking subsequence, uniformly convergent to a constant function. And in addition, since for each m we have an instant such that Rm of this instant belongs to the boundary of V, we can see that the limit, the constant limit of this function, is a point at the boundary of V. In this case, the boundary of V is just 2 points, 1 plus minus alpha. Okay? If now we use that Rm is a solution of this differential equation, then through the by the integral characterization of solution of differential equation, we know that Rm of theta is equal Rm of 0 plus the integral between 0 and theta of epsilon m lambda n f of Rn of s epsilon m ds. Okay, we know that. But we also know that Rm is 2 pi periodic. That means that when I compute Rm of 2 pi, it must coincide with Rm of 0. Then this vanishes and this integral has to be 0. However, since we know that epsilon m and lambda m is not 0 for every n, then this integral has to vanish. Okay? So we know that the integral between 0 and 2 pi of this function computed at Rm of theta is equal to 0. Okay? So now what we do is to substitute the expression of f in this integral. Okay? We call that this is the expression of f. Careful here, because we know that if we integrate this term between 0 and 2 pi, this goes to 0. But notice that in this case, I'm assuming that R is constant. But the integral I'm doing here is not taking R to be constant. R is a function. It's Rm of theta. So we do not have guaranteed that this integral is 0. Okay, so careful here by just taking this integral as equal to 0, because it's not. Well, the idea now is to compute this integral. We know that it's 0, the whole integral. Then I will isolate this integral here. Okay, I will isolate in the next page this integral. So that's what we have here. The integral between 0 and 2 pi of Rm of theta cubic root of Rn of theta square minus 1 multiplied by sine square of theta is equal to this expression. So here we have 1 divided by epsilon m power to k minus 1 multiplied by this power series of epsilon. Okay, so the idea here is to see that the right-hand side of this relation goes to 0 as m goes to infinity. So here we have to be careful because, for instance, sorry, because we have an epsilon m power to I minus 1. So for instance, if I is equal 1, then we do not have epsilon here, and we have an epsilon in the denominator. So we have to be careful in order to conclude that this goes to 0. These functions, gn, ij, I'm just changing the names in order to simplify the expression. So this is this integral here. So what I'm going to prove now is that gn ij is a function of order epsilon n power 2k. That's what I'm going to prove. And to do that, I'm going to use the integration by parts, okay? Because if we call Rmi by u and cosine power to j times sin by dv, okay, we know that du, this is equal to u times v computed between 0 and 2 pi. This goes to 0 because the integrand is periodic, okay? And I have minus the integral between 0 and 2 pi of v du, okay? V, the integral of the primitive of this function is given by cosine minus cosine j plus 1 of theta divided by j plus 1, and the derivative of this function u is just I that multiplies Rn of theta I minus 1 R prime n of theta. Okay, so that's what I'm writing here. So applying integration by parts, I had forced the appearance of the derivative of Rn, and I know that Rn is a solution of this difference equation, which has an epsilon, a factor epsilon here. Okay, so substituting the Rn by its value, it's epsilon m lambda m times f of theta Rn of theta epsilon n, and also substituting this function, the value of the function computed at this point, we conclude that gmij is given by this sum. Okay, and in this sum we already have this power of epsilon n. Okay, this starts by 1, and then we have proved just by this first step that gmij is an order epsilon n. However, here we have written this function in terms of itself. Okay, it's not itself because I'm changing this this index, but the property of it to be order m does not depend on the index ij. Okay, so we can repeat this procedure recursively in order to conclude that this function is an order epsilon m power 2k. Okay, we cannot improve this order because when I do the substitution of f, then we already have an order epsilon m power 2k. So this cannot be improved. Then I can just increase the order of gmij until epsilon m power 2k. Okay. Well, so let's see. We proved that this integral, when I substitute this information here, when I substitute this information here, each one of these functions are power epsilon to k. This is the minimal exponent here. Since I'm dividing by epsilon k minus 1, what we get is an order epsilon n. Okay? So this is what we get. So taking the limit here for epsilon going to infinity, we know that this function are uniformly convergent to a constant function R0. Okay, so the integral with the limit here, we can commute this operation. So the limit of this integral is the integral of this limit. Okay, and in the right hand side it goes to 0. Okay, so what we conclude is that the integral of R0 multiplied by the cubic root of R0 squared minus 1 times sine squared of theta, this integral is equal to 0. However, we can compute this integral. This integral is equal this function. And we know that this function vanishes only for it's equal, equal 0 implies that R0 belongs to plus minus 1, 0. Okay? And we know that it does not happen because R0 belongs to the boundary of a V, and the boundary of a V can be only 1 plus alpha and 1 minus alpha. So this cannot happen. Therefore, hypothesis H must hold for the difference equation that we are dealing. And theorem 5 can be applied in order to conclude the proof of this theorem and obtain the existence of a periodic orbit converging to SE1 uniformly as epsilon goes to 0. So this is the a complement of the last lecture, which was missing. Here I have run it, a mathematical simulation of this differential equation. We can see here the existence of the limit of a periodic solution here, and the simulation was done for k equal 2 and epsilon equal 0.1. I also have simulated the displacement function varying k for several k's. Okay, so this first simulation is for k equal 1, and here we have epsilon equal 1 over 20, and here epsilon equal 1 over 100. We see that the displacement function intersects the axis x close to 1, and when we make epsilon small, it approaches to 1, and the displacement function becomes vertical. The same happens for other values for k's. This is the same happening here. And in the last case, when I taking k equal 3 and epsilon equal 1 over 100, we start to get some numerical issues here. So we stop it. Well, okay, so we have studied the averaging method for studying periodic solutions, for smooth distance, for Lipschitz continuous systems, and for continuous systems without assuming the Lipschitz conditions. Now, let us study the averaging method for studying periodic solutions of discontinuous piecewise smooth differential equations. Okay, so let us consider D an open bounded subset of an Euclidean space. S1 here will be the quotient of R by the integer t. It's just to simplify the decomposition of the space that I will do here. It's the same as assuming that all the functions are t periodic in the time variable. Okay. So we will consider disjointed subsets Sj of S1 times D, and we will assume that at Sj, the boundaries of Sj are piecewise decay embedded hypersurface, and we denote by sigma as the union of the boundaries of Sj. Sigma will be our discontinuity set. Okay. Well, so we also consider functions fi and r given by this sum. So here I'm assuming that fi is the sum between j equal to 1 up to n of the characteristic function of the closure of Sj computed at Tx multiplied by a function Fij, the same thing for the remainder. So what does this mean? The characteristic function, as you may know, is defined as 1 if Tx belongs to the set A, and 0 if Tx does not belong to the set A. Okay, so the characteristic function of Tx associated to the set A is defined like this. So here, what I'm defining here is a function which takes the value of Fij if Tx belongs to the closure of Sj. Okay, so I'm decomposing the domain and dividing the domain into subsets, and in each one of these subsets I'm consider a distinct function, okay, in order to define this Fi. So here all the functions Fij are T periodic in the variable T, and we will also assume that they are all smooth, sufficiently smooth, okay? We can also produce results in less regularity context, but here we will just assume that they are all smooth. And we will consider differential equations in this standard form, the same that we have considered before. The only difference here is that we are allowing the functions to be non-smooth. Okay, so for this standard form, we will assume the Lipschitz conditions. Okay, sorry, Lipschitz conditions, no, the Filipov conditions. So this is a Filipov system. Filipov system, which is just a piecewise smooth system plus Filipov's condition. Okay, so at this point, I think that you have heard a lot about Filipov systems in other courses. Then we can just use the concepts and definitions of this kind of system. Okay, so what we are doing here, we have our domain. Let me draw here. This is our D, and we also have our S1. So let's just consider an identification of these two straight lines, and then I'm decomposing this set into other sets. Okay, and in each piece I am considered a let's say a distinct differential equation. Okay, F1 for instance, F2, F4, and F5. Okay, so in each one of these pieces I'm consider this differential equation, and the solution of this differential equation is given by the Filipov's convention. Okay, so this is the context we are going to work now. Okay, so the main hypothesis in order to introduce the averaging method is in this context is the crossing hypothesis. So it says that there exists an open-bounded subset C contained in the domain D, such that for epsilon equal to 0, this curve intersects the discontinuity set only in crossing region. Okay, so let me just copy this figure. Sorry. Let me paste it here. So I am assuming that there exists a region C here, where the intersections of the constant curves with the discontinuity set, take at this point and this point, happens only at the crossing region. So here I'm assuming that all these points are crossing region for the unperturbed system. So note that this line, this straight line, is an orbit of the unperturbed system, because the unperturbed system is x equal to 0. So the constant functions are the solutions of the system, and in order that, since this is the direction, okay, so in order that this intersection happens only at crossing regions, then we just have to assume that it does not, that the discontinuous set does not have something like this. Let me just draw here, for instance, at this point, this line wouldn't intersect the discontinuous set in a crossing region. Okay, so we couldn't have things like these two, because here we would have a sliding region. Okay, so we just have to assume that for a region of the initial conditions, the trajectories of the unperturbed system, that is, these lines, intersects transversely the discontinuity set, discontinuity manifold. Okay, so since the crossing region is a genetic property of our difference equation, when I take epsilon sufficiently small distant from 0, then this property still holds. That means that when for the initial conditions starting at C, and the solutions of the perturbed system for epsilon distant from 0 will still cross the discontinuity manifold only at crossing region, at crossing points. Okay, so in this case we can study these solutions just by taking composition of solutions of smooth systems. Okay, so under this hypothesis, the first order averaging method says the following. So we define the first order average function. It's the same that we have defined before. F1 is just the integral between 0 t and the period of F1, and we have this first theorem. In addition to hypothesis, the crossing hypothesis, if Z star belonging to the set C, where the crossing hypothesis holds, then if Z is a simple 0 of 1, then for epsilon sufficiently small, the difference equation 1 admits a unique T-periodic solution converging to Z star as epsilon goes to 0. I'm not going to explain the proof of this theorem now, because we will study a more general this in a more general context. Okay, so but the idea is simple. Okay, let's just draw what's happened in in this set. Okay, so this is the set. We know that every solution of the unperturbed system reaches the set of discontinuity only in crossing regions. Then this is the same will happen for solutions of the perturbed system. We start here, then we reach the discontinuity manifold in a crossing region. Then we can make the composition, and we can work just with the compositions until the period. Okay, so here we can define the displacement function of this differential equation. Okay, and then work with the expansion of this differential equation in power series of epsilon and define the bifurcation functions. And we see that the first order bifurcation function coincides with the average of F1. Okay, so this is the idea. We'll explore this idea in a more general context. Okay, so let's see an example. It's a discontinuous perturbation of the harmonic oscillator. Okay, this is the same. We call that, in order to detect periodic solutions after the first order analysis, we had to assume that the perturbation was cubic in the smooth context and piecewise quadratic polynomial in Lipschitz, in continuous but Lipschitz context. Okay, so here, if we allow discontinuities, then we will see that a periodic solution appears in a first order analysis, even if we assume that our perturbation is piecewise constant, is a piecewise constant function. Okay, so here, let's take G1 equal beta plus if y is positive, beta minus if y is negative. We compute the normal form, the standard form. We apply the transformations. We can compute the first order average function. Note that in this case, the discontinuity manifold is only happens only at time. Okay, this is the standard form. The discontinuity is 0, pi over 2, and 2 pi. Okay, so if we draw, this is the discontinuity set. So we have pi divided by 2 and 2 pi. Okay, and for this discontinuity manifold, the orbits of the unperturbed system always intersects the discontinuity manifold transversally. So this property remains, persists for the epsilon small. So the crossing hypothesis is satisfied in this context. And when we compute the first order average function, we obtain this linear function, and of course we can solve this linear function. We can solve this linear equation and obtain a simple zero, which belongs to the domain as long as B1 multiplied by this difference is positive.
Okay. Sorry, Douglas.
Yes?
One comment. You have selected P over 2, but the integral is between 0 to pi and then pi to 2 pi.
Yes. Yes, sorry. It is wrong here. Thank you. Here, applying the first order averaging method, we see a bifurcation that has been explored by John Torregrossa and also Thiago, which is the Hopf bifurcation, because we are breaking the fold-fold it's not the fold because there is a collapse of two singularities here, and then we are just breaking this point, and when we do that, it appears in this case an escape region, and it always appears a limit cycle bifurcating this point. In this case, the Hopf bifurcation parameter is this one, beta plus minus beta minus. However, in our case, our distinguished parameter, the small parameters, is epsilon. Then fixing beta plus minus beta minus, we see the existence of a periodic solution converging to a circle of a specific radius. It's not goes to zero when we vary epsilon. Of course, if we vary this parameter, this limit cycle will converge to the origin. However, fixing this parameter and varying the epsilon, our limit cycle converges to a circle with a given radius like this. Okay, so this is the mathematical simulation. Here we can see the fold points. I'm taking two very close points here and drawing the trajectories, the forward trajectories of those 2 points. Okay, so here we can see the non-uniqueness of solutions, of future solutions for points on this segment. Okay, and I'm also running the simulation for a point outside the region delimited by the limit cycle, and you see that this trajectory converges to this object. So we have a limit cycle here. Okay, just taking a smaller epsilon, we see that the limit cycle actually becomes closer and closer to the circles of a given radius. Okay. Well, so how about the second order averaging method? Recall that the second order averaging function was given by this expression, and we wonder if this function also controls the bifurcation of limit cycles in discontinuous systems. And we saw and we discovered that actually this function do not always control the bifurcation of limit cycles. We have to impose a new hypothesis in order to have that this second order averaging function control the limit cycles of the previous system that I have introduced. Okay, so the hypothesis is saying that this vector 0 y1tz, we call that y1tz is just this expression. Okay, so this vector has to belong to the tangent space of the discontinuity manifold at the point tz. Okay, tz, it must happen for every t in sigma in order to this theorem holds. Okay, so if this hypothesis is true, then simple zeros of F2 provides the existence of t-periodic solutions converging to z star as epsilon goes to 0. Okay, this can be seen as a string hypothesis, but it's actually providing that this function is actually the bifurcation function for this case, provided that a condition between the perturbation, because y1 depends on the perturbation, and it provides a relationship between the perturbations and the geometry of the discontinuity manifold. Okay, so this property has to be satisfied in order that F2 controls the bifurcation of periodic solutions for these systems. Let me just comment here that this property always hold in some very very explored case in the literature. Usually when we are working, at least 7 years ago, when we are working with piecewise smooth difference equation, we assume that the set of discontinuities are, for instance, lines for planar case. The set of discontinuities are usually assumed to be lines or rays crossing the origin, right? We usually do that. We consider piecewise linear differential, piecewise differential system where we have a line, for instance, passing through the origin as the set of discontinuity. Also, in that time when we produced this paper, we had works with this configuration of discontinuous manifolds. So in this case, for this case, these hypotheses always hold, okay? Because when we are working with planar systems with rays of discontinuity, when we perform a polar change of coordinates, what you get are discontinuous systems, but the discontinuity are located only at the time variable. And for this kind of system, this condition always hold. And why that's true? Let's see. Consider here the time variable and assume that the discontinuity are given by are given only at the time t. So we do not have any anything like this that varies also with the spatial variable. In this case, if we consider a point at the discontinuity set, since it's a straight line, the tangent space of this discontinuity set is the line, is the space itself, okay? Of course, we have to translate it to the origin, but this is the, if this is P, no, let me just take T and X. This is T and this is X. If it is the tangent space of the discontinuity manifold at Tx, then this vector always belongs to the tangent space because this vector always has zero in the first entries. So this vector is something like that. Okay, this is the vector 0, y1, t, z. Of course, we have to see the origin of our space at this point. Okay, so in this situation, this hypothesis always hold. Okay, this situation when we transform our system and the transformed system has discontinuity only at the time variable, then hypothesis HB2, that as we call it in 15, always hold. Then the second order averaging method can be applied. And actually, in this hypothesis, any order of the averaging method can be applied. Okay, I will comment in a few minutes the high order version. Okay, just to comment an application of the second order averaging method.
Douglas, would you like to be a break or after this example, or what do you think?
I think that we could have a break after the example. Perfect. Is that okay?
Yeah, perfect.
Okay, so before the break, let me just comment this example. So in 11, we studied these three families of quadratic homogeneous center, and we want to detect the bifurcation of limit cycles using the averaging theory of first and second order. Okay, so we perturbed these families of quadratic homogeneous system in this family of systems. So we consider first order perturbation, second order perturbation. The perturbations were quadratic, perturbations, and the set of discontinuity were lines, okay, like this. So for the second order average function, the hypothesis HB2 that I have explained before holds in this case. So we don't have we don't need any other kind of theorem. We can just use the average functions that we have already defined. Okay. So let me comment that the idea here was to find the maximum number of limit cycles, or at least lower boundaries for this maximum number of limit cycles for these three kind of centers. Let me comment what we found for these systems, okay? Z2, for these families, Z2. So the idea, in order to use the first and second order averaging theorem here, is the same. We have to transform the system into another system in the standard form for applying the averaging method. So the first thing we have to do is linearize the system. So since they are homogeneous, they can be conjugated with the linear center, and the conjugation, the linearization, were stated in this work, the Zoladex work, Zoladex paper, and using this transformation, the differential system Z2 is transformed into this linear center. Okay. Then after transforming the system Z2 in a linear center, we apply the polar coordinates in order to write the system in the standard form. However, when we do that in this case, what we obtain are a differential system. However, the right-hand side of the differential system were piecewise rational functions, not polynomial anymore. Okay, so we have this function written in the standard form, but now we have those quotients here. Okay, so the functions A1 and A2 are piecewise functions given like this. The function A1 are polynomials of degree 3. Okay, then we have to compute the first and second order average function for this family of differential equation. Okay, doing so, when we compute the first order average function, we obtain that F1 is written as a combination of 8 functions. Okay, this coefficients Kn depends on the initial coefficients of perturbations, and the functions Fn are given by this list of functions. Then you can see that when you change the example that you are considering, if we consider things more complicated than the linear center, then the functions that you obtained starts to be more complicated. Okay, so we have some quotients here, then we have other functions that depends on L2, which is a logarithmic function of a quotient, and also these other functions phi tilde, which are given as this difference, and the function phi is something like that depends on a square root and an arctangent of a square root multiplied by an arctangent. Then just for you to note that the things starts to become stranger. Okay. Well, so what we have done here, the idea was to expand this function in power series of ρ around ρ equal to 0, and doing that we saw that Fi for I equals 0 until 5, this starts as ρ power I plus 1, and the last two functions, f6 and f7, started as a power 8 of ρ, and f7 a power 10 of ρ. With this, we can see that this set of function is an ECT system, an extended complete Chebyshev system in a neighborhood of the origin. I'm not going to explain this concept here, but if anyone is interested in those techniques, can check these papers, these two papers, okay? So this implies that in a neighborhood of the origin for ρ near 0, we can find 7 zeros of our first order average function. We can find coefficients, suitable coefficients k, in order that f1 has 7 zeros near ρ equal to 0. Okay, so these 7 simple zeros. This means that the averaging method provides 7 limit cycles. I didn't say, but this is done assuming that the polynomial perturbation vanishes at the origin. So now performing a Hopf bifurcation here, just adding the constant term of the perturbation, we get another limit cycle. This is something that João Torregrossa has already explored in his talk. Okay, so averaging method plus Hopf bifurcation provides 8 limit cycles in a first order analysis. Then, after that, we pass to a second order analysis. And in order to do that, we have to assume minimal conditions in order to ensure that the first order averaging function vanishes. Notice that since we have that the first order average function is given by this sum, this function is identically 0 if and only if all these coefficients are 0. So here are the minimal conditions in order to f1 to be identically 0. Okay, that's what I'm saying here. So assuming conditions on the perturbation in order that f1 is equal to 0, we compute the second order average function. Okay. In this case, the second order average function can be decomposed into integral. Okay. The first one can be computed in a very similar way than the first order average function, but the second part of this integral is more complicated and actually can't be computed explicitly because we have to compute the derivative of a quotient and multiply this derivative by the integral. Okay, here we do not have 2π, here it's a function. Okay, and multiply this by this integral. Then the denominator is 1 plus r cosine theta square of the sum, and the numerator appears functions like this. In particular, so we have r theta cosine sin lambda. Lambda is this logarithmic function, and in particular, when we have to integrate this phi, we cannot do. Okay, we cannot compute this integral. Okay, so unfortunately, this part of the function f2 cannot be explicitly computed. So that's what I was talking, and also Joan has also commented this, that although we have a nice formula for computing all the average functions, when you are working with explicit vector fields and difference equation, it's a hard thing to do, to compute this integral, depending on the case that you are working. For instance, in this case, in order 2, homogeneous centers of order 2, we cannot compute this integral. Okay, so we have to work with this function without computing the integral explicitly. So the idea here, and it was enough for our purpose, was to expand, before compute the integral, expand the integrand in Taylor series of R in this case. And then we computed the integral, okay? When we did that, we conclude that F2 can be written as a sum of powers of R, and then after a lot of algebraic manipulation and also using the Poincaré-Miranda theorem, we were able to find a transformation in the coefficients such that F2 can be written like this. Okay, so we transform the parameters Fi into parameters Di, and we see that these parameters Gi depends on the initial parameters of perturbations in a surjective way. Okay, that means that if I change the original parameters, then these new parameters change surjectively in a neighborhood, we write surjectively in a neighborhood of the origin of R60. Okay, so again, we can ensure, for instance, using the preparation theorems, for instance, we can ensure that this function has at least 15 simple zeros around R equals 0. Then the average method provides 15 limit cycles. Here, I'm still assuming that the polynomial perturbation vanishes at the origin. So after obtaining 15 limit cycles, we can add the independent coefficient and obtain an additional limit cycle through a pseudo-Hopf bifurcation. Then we obtained a quadratic system with 16 limit cycles. And I think that it's still the best lower bound so far for the number of limit cycles in quadratic piecewise system with two zones separated by a straight line. I don't know, perhaps Joan could inform us if this is still the best lower bound. I saw that in his talk yesterday, they showed that locally we get at least 13 limit cycles bifurcating from a weak foci. And this is greater because we are studying limit cycles bifurcating from the periodanus. Okay, so I think that we can stop here and return in 10 minutes. Okay, so just to comment, the high order averaging method, as we have stated for the functions that we have already defined, works in the non-Smith context as long as the discontinuity only happens at the time variable. Okay, if you have, for instance, a piecewise linear system, a vector field, and you can transform this non-Smith vector field into a non-autonomous differential equation with discontinuous, which is discontinuous and only at the time variables, then you can apply the formula for the averaged, for the high order average functions as we have defined it without any problem. Okay, you can compute and it will controls the bifurcation of periodic solutions. But what happens in a more general case? What happens, for instance, in the second order bifurcation when the hypothesis 8b2 that I have talked about does not hold? So let us consider difference equations, piecewise difference equations given in this standard form. So this is the same that we always have, but here Fi are defined as this function. So note that in this context, the characteristic function was taking time, but it was constant. Okay, so if theta belongs to this constant interval, then Fi is equal to Fij. In this case, these intervals depends on the variable x. Okay, so I'm assuming that those functions theta j satisfies these inequalities, cannot intersect itself, and they are just smooth functions on the domain D. Okay, so the idea, I have a picture. I have a picture here. Let me just comment this picture. The discontinuous set are given now by these curves. Okay, so this is a graph. However, the domain of the graph is the spatial spatial domain. Okay, so this is saying how the time varies with the spatial variable. Then I'm defining the discontinuity manifold by these graphs. Okay, and again, in each one of these sectors, in each one of these spaces, I'm defining a specific equation, Fij. This is another way of write this function. Okay, so Fi is equal Fij if t, the variable t, is belongs to a certain interval that depends on x. Okay, so for this kind of system, we obtained the second order bifurcation function that we call it Markov function too, and we saw that this bifurcation function is equal to the average function that we have defined plus an increment, an F2 star, okay? And the expression of this increment is given by this. So this is interesting to note that, for instance, if the function Fi is continuous, F1 is continuous at this point, then this difference is equal to 0, because we have our theta j of x here, that's the curve. At this side we have f1 j minus 1, and at this side we have f1 j. Okay, so if at some region the function f1 is continuous, then this difference vanishes. Okay, so also this increment vanishes. Okay, so this increment depends on what we call it by jump of discontinuity. Okay, now this term is related with the hypothesis HB2. Let's just recall the hypothesis. Oh, sorry, it's here. This hypothesis HB2, which is saying that this vector must belong to the tangent space. So let's see what's happening here. Note that this integral is y1 computed at theta jx x, and this point is a point of the discontinuity manifold. Okay, and this theta gives the discontinuity manifold locally at least as an inverse image of 0. Actually, x t minus theta j of x minus 1 of 0 is contained in our discontinuity manifold. Okay, then this derivative is in some way defining the tangent space of the discontinuity manifold, because if we call this function by, I don't know, a t j of tx, then the discontinuity manifold, the tangent space of the discontinuity manifold, is just the kernel of the gradient of tj. Okay, so saying that this product vanishes is equivalent to say that hypothesis 8b2 holds, because hypothesis 8b2 is telling us that this vector ytz belongs to the tangent space of tz of the discontinuity set. And this is equivalent to say that this product is equal to 0. So this hypothesis implies that F2 star vanishes. Okay, so in this case, we do not have any increment, and the bifurcation function of order 2 is just the average function of order 2. Okay, so for this bifurcation function, we have the usual theorem. If we have a simple 0 of M2, then the difference equation 11 has a t-periodic solution converging to this 0. Okay, so in order to prove this theorem, what we have to do is study the trajectory of the Filipov system. Okay, so this is just a representation of the Filipov system, and the solution of the Filipov system is given as the concatenation of solutions of several differential equations. Okay, so here, for instance, in this zone, we have F0, then here we have F1, Fj minus 1, Fj, and so on. Here we have Fn minus 1 and Fn. Okay, so in each piece of this figure, the trajectory of the Filipov system is a solution of a differential equation, which in the right-hand side we have this expression. Okay, so that's what I'm writing here. The derivative of Fj is equal to Fj computed at this point. Okay. We also have another information here, which is the initial condition. It's not any solution of this difference equation, but we have to fix the initial condition. So here we have to be careful with this definition, because it when one see this, one can think that for t equals 0, the value is for t equals 0 is equal to x0, but it's not true. Okay, this is just indexing and explicit the dependence with the initial condition, but I'm not saying that for t equals 0, this expression is equal x0. What we have here actually is that phi 0 for t equals 0 is equal to x0, and here we have the phi j t x0 epsilon. Then in order to have a continuous trajectory, what is true here is that phi j computed at this time that we are calling alpha j. Okay, so phi j computed at alpha j is equal to phi j minus 1 computed at the same time. So we have this kind of recursively defined sequence of differential equations which provides the trajectory of the Filipov system. Another thing that we can notice in this figure is a relationship, an implicit relationship for this function alpha j, which is the time that this piece of the trajectory intercepts this graph, theta j. So here notes that alpha j, since it is corresponding to this point, alpha j is equal, it's in this curve, so it's equal to theta j computed at this x, which is this x. It's not x0, it's close to x0, it's not x0, but it's exactly this function evaluated at t for t equal alpha j. So we have this implicit relationship for alpha j. It does not provide a formula for alpha j, but we can compute all the derivatives of alpha j implicitly by this relationship. Okay? Well, so what we have to do now is just try to expand in Taylor series the displacement function. Okay, so we have our trajectory for a time t, it reaches the section that we are interested, and the displacement function is just this difference, is phi. Note that phi t for t equal capital T is phi n. Okay, this is important too. So this is phi n, is the last piece of our trajectory computed at t x0 epsilon minus x0. Okay, so this is the displacement function. And I want to expand this displacement function around the epsilon equal to 0. Okay, so using the integral characterization of these solutions, we can write the solutions of the recursively defined sequence of difference equation like this. The last one is given by this integral. When we basically solve this recursive, we can see that phi n, the last piece of the trajectory, is equal x, the initial condition, plus the sum of integrals. I'm just substituting the recursively formula for phi j given by this here, and doing so recursively we obtain this expression for phi n. And as I told, the displacement function is just is given by this expression. Then the idea is to expand the displacement function like this. Okay. Well, since we know that the displacement function is this difference, which is equal to the sum, what we have to do is expand this integral now around epsilon equal to 0. Here notes the difference between this case and the case when the discontinuity happens only at the time variable. If the discontinuity happens only at the time variable, then this extrema, the extrema of the integral does not vary according to epsilon. Okay, it's always constant. Then we only have to expand this function. That is exactly what we have done in the smooth case. Okay, so that's why in this case of constant of discontinuity only at the time variable, that's why in this case the bifurcation functions coincides with the average function that we have already defined. In this case, we have to be careful. So the first thing we do is to expand this integral. It only varies the upper extrema here. This is the first piece of this integral. When we do, we just use for instance, the Leibniz rule for integrating derivative here, and we get that this the first order here and the second order. Note that in the first order we do not have the derivative of the function alpha does not appear here. It's just the integrate between 0 and theta 1 of our of f1. So that's why the first order average method always coincides for any kind of piecewise differential system, because the dependence of the geometry of the discontinuity manifold does not appear in the first order. Okay, it only appears after the second order. Note that here is the term is a term corresponding to the average function that we already have. If you look at the formula of F2, you see the derivative of the vector field multiplied by y1, which is exactly the derivative in epsilon of the solution, plus the second order term of perturbation. So this term is new here, and it only appears after the second order. Okay, the same can be done. Oh, okay, so here we have this derivative, and this derivative can be obtained by the relationship that we get for alpha 1, for alpha j. Okay, this relationship, we can compute derivatives of alpha j. And doing so, we conclude that this derivative is the derivative of theta 1 multiplied by this integral. Repeating this procedure for the others integrals. Okay, here there is it's a little bit different, because in this case the lower extrema didn't depend on epsilon, but here it depends. But the only difference here is that it appears two terms, okay, depending on theta, on the derivative of theta. When we put everything together, what we obtain is exactly this expression for M1 and M2, where F2 star is given by this expression. Okay? So an application, okay, so not application, but this result, this second order result was extended for high order bifurcation functions. We obtained all those expressions in this work, and in this work we studied bifurcation of limit cycles in piecewise linear system with two zones divided by an algebraic curve. Okay, so let me just comment this result. It's interesting because it's an application of the previous averaging theorem. So Hn here for us denote the maximum number of limit cycles that planar piecewise linear systems with two zones separated by this curve can have. Okay, so n here is the degree of the curve of separation, the discontinuity manifold. And in order to study lower bounds for this number, we consider the perturbations of linear centers. Okay, and I'm commenting some previous results on this about this problem. However, it's resumed. Sorry, it's summarized in this table. Okay, so for n equal 1, it's just a line of discontinuity. It's a work of Joan and Claudius, Claudio Buzzi e Claudio Pessoa, applying averaging theory or something similar. They obtained 1, 0 of the first order bifurcation function, 1, 0 of the second order, 2 for the third order, and 3 after the fourth order up to order 7. Okay, so ML here denotes exactly the number of zeros that the average function of order L has when this is the first or the first non-vanishing average function. Okay, so this is the program that I have explained. We compute the first one, assume conditions on the perturbations in order that the first one is identically 0, then we compute the second one. And we, in this process, we will study the maximum number of zeros that each one of these functions has. So this table is summarizing this result. So for a parabolic curve of discontinuity, we had 3 limit cycles before the work 1, and for a cubic, we already have 3 and 7 limit cycles, 7 limit cycles in a second order analysis. For n greater or equal than 4, we didn't have any information about that. So in this paper, using this higher order bifurcation functions, we were able to more or less complete this table. Okay, so we provided results, and the interesting thing that we have to check here, to see and to note in this table is this last column, because these numbers actually provides lower bounds for Hn. Okay, so when we have a parabola of discontinuity, we have 4 limit cycles, and these 4 limit cycles can be observed in a second order analysis. Okay, and it keeps 4 until a 60th order analysis. For a cubic curve of discontinuity, we have 8 limit cycles, at least 8 limit cycles. Okay, and it was 7 until order 5, and in order 6 we were able to improve this number. For any greater than 4 even, we have 7. It's still persists the same number as the second order analysis, and for any odd and greater than 5, we obtained 9 limit cycles, and these 9 limit cycles appears in order 6. Okay, well, I think that I have 15 minutes, and let me just comment, and I'll comment, some results do not appear here, some other problems that can be approached by averaging method. Okay, so the first problem that I would like to show here is the bifurcation of periodic solutions, but now from families of periodic solutions. Okay, in this situation, what we have is that the unperturbed system is not the trivial one as we had in our standard in our standard form. That epsilon appears multiplying everything, and when we take epsilon equals 0, then we have the trivial difference equation x prime equals 0. Here we have an unperturbed term. X prime equals F0 is the unperturbed system. And we assume that for this unperturbed system, we have a manifold that can be open or bounded or closed, a manifold of periodic solutions. And the question here is, the question is the same. If any of the periodic solutions, or what are the conditions on the perturbations in order that some of the periodic solutions of the unperturbed system persists as periodic solutions for epsilon distinct from 0. So for this problem, I have, for convenience, I have collected some references here where, for instance, for a smooth case and a first order analysis of this problem, you can find the results and examples in this paper. It's a paper from Buica, Jaume, and Jean-Pierre François. A second order analysis can be found here. I think that those are works of Buica, Gibri, and Jaume. A third order analysis, I have a work with Jaume Gibra, and at any order analysis are some works from mine, also Jaume and Jaume Gibra and Murilo Cani. So results about this problem in this Muse context can be found here. In the Lipschitz continuous context, you can find results of first order analysis. Here it's a work of Gibri, Makarenkov, and Buica. And for its continuous systems, you can find some results here. It's a work of mine with Jaume and Camila Rodrigues. Okay, so just to illustrate the idea here and what can be achieved by these results, if we consider this 3D polynomial differential system, and if we perform a cylindrical change of coordinates, this system can be written like this. Okay, and here for theta dot, the derivative of theta, we see that it starts with 1, and we have epsilon that multiplies something here. So the same thing that we have done in the second lecture of this course, we can, since it's distant from 0 for epsilon sufficiently small in a controlled domain, of course, and we have to attain in a compact set, we can take theta as the new independent variable. So this differential equation can be studied in terms of this differential equation. And you see that for this differential equation, we have a non-trivial unperturbed system, because for epsilon equals 0, we have dr d theta equals 0, but z d theta is equal to z. The perturbations here are given by these functions. Okay, so when we see when we study the unperturbed system, we see that it's not right, it's the solution of the unperturbed system is given by this. Okay, so if we take z0 equal to 0, then this function is constant, r0, 0, that is periodic. So for this, if we consider this manifold, this is a manifold of periodic solutions, actually a manifold of initial condition that provides periodic solutions of this differential equation. Then we can use the results of the previous works that I have showed in order to obtain this proposition, for instance. So we can ensure that for epsilon positive sufficiently small, this differential equation and consequently this vector field has a periodic solution satisfying this property.
Sorry, Douglas, this t is the time or is the angle here?
Here's the time. Here's the time. We come back with the transformation.
Thanks.
Okay, so this is the just a comment and an example of this problem, and let me show you another problem, but now relating bifurcation of invariant tori using the averaging method. So all the objects that we have found here are invariant objects because are periodic solutions, but it's as a manifold, it has dimension 1. Then we wanted to pass to invariant manifolds, the existence of invariant manifolds, but with higher dimensions, in this case dimension 2. Then in order to study this problem, we consider differential equations given in this standard form, but here we have 2 distinguished parameters. In the standard form that we have studied before, we had only the small parameter, which was epsilon, but here we have epsilon and also mu, which are 2 parameters. So we consider 2 parameter families of non-autonomous differential equations. This is written in the standard form according to epsilon. Then we can compute all the averaged functions here. Okay, I assume that it's smooth and all the good properties. Okay, so if L is the index of the first non-vanishing averaged function, we can consider the truncated averaged system. Okay, this is GL, but it's also, we have seen, FL x mu divided by T. Okay, And the result in 9 is more completed and stronger than the one I'm going to state here. But just the simple result that we have in this situation is that if this truncated average system undergoes a Hopf bifurcation, and by Hopf bifurcation, I'm talking about when I consider the parameter mu. Okay, then we change the parameter mu, and when mu passes through a critical value, mu star, for instance, then the system, the truncated average system, undergoes a Hopf bifurcation. So here we have to compute the Lyapunov constant. We have to all the things that we have to do when we want to check if this system, autonomous system, undergoes a Hopf bifurcation. Okay, but if it happens, then this system undergoes a torus bifurcation. So the bifurcation of a limit cycle from the origin, the bifurcation of a limit cycle from some point, from some Hopf point of this system provides the bifurcation of an invariant torus of this system around a periodic solution. Okay, and this is the simple result that I can state here. We can use also in 9, it is explained, but we can use also the high order terms. It's also the high order averaging, but we can also use, for instance, the orders greater than L unto K in order to improve this result. Eventually, we do not have a Hopf bifurcation for this system, but if you add a perturbation, then we get a Hopf bifurcation. We can do that, and it still concludes the existence of invariant tori for the system 27. So we applied this theorem for the Oscillator system. I'm not going to explain the details of this application because we do not have time, but we were able to prove the conditions on the parameters of the Oscillator system such that we get the existence of an invariant tori for this vector field. So this is explained here, and in the statement 2 we get the existence of a unique invariant torus bifurcating from a periodic orbit. Then we can control the stability of the periodic orbit, the stability of the torus, etc. Here is just some mathematical simulation of this torus for some concrete values of the parameters. Okay, L1 is the Lyapunov coefficient here that has to be distinct from 0 in order to guarantee a Hopf bifurcation. And I'm drawing here the Poincaré map, okay, of the Oscillator system. And this invariant curve in the Poincaré map corresponds to an invariant torus of the vector field. This is just another example for some concrete values of the parameters. We also have the existence of an invariant torus here. Okay, so I think that is what I want to explain for you. I hope that you all enjoyed this lecture. Thank you very much.
Thank you very much, Douglas. There is some question in the audience. There is someone who is interested to ask Douglas.
I only said that I like very much this result about invariant tori.
We are still working on results like that. We are trying to improve these results because here we needed this Hopf bifurcation, but I think that it's not needed a Hopf bifurcation. But the proof that we have on here involves to detect a Mark-Zucker bifurcation in the Poincaré map. So I needed the half bifurcation, but I think that it's not needed. If we find a limit cycle in some suitable conditions in the first order average function, the first order average function, no, the first non-vanishing average function, then you always have an invariant tori in the differential equation.
Probably you are right, yes.
More questions? If not, I have a comment. Can you move to the slide that you provide a lower bound for the Hn?
Yes.
In the linear versus linear. This is the n for you means the degree of the separation curve, or just the n for x to power n?
No, it's for this curve.
Yeah, because if you assume that the curve is a polynomial of degree n, then Hn is at least n over 2 up to first order. But it is, I think that if you can improve, if anybody can improve a result that together with Armengol and Xiangzhang, I think that our lower bound at least should be doubled if you work with second order. But it is quite hard, eh? But it would be nice to have a good lower bound in terms of the degree in the linear case for at least of order n, not n over 2, at least
sorry, you just consider an algebraic curve of a fixed order, because in this case it could have the orbits of the unperturbed system could eventually intersect this curve several times.
Yes, this is the problems that Jaume explained this morning, no? That you need to control something more. Hmm?
Yes, but it could be, of course.
Because if you don't bound the degree, you can think, for example, that the discontinuity line is, for example, you know perfectly, no? The sinus, for example, and then you have infinitely many.
Yes.
Well, then I will stop.
One comment, please, about this table 2. You separate the curve y equals x power to n, 2 linear centers, no? This is the case, no?
2 linear centers, yes.
Yes. Then I have a paper with Xiangzhang that we provide upper bound, not lower. We don't use averaging, but we provide upper bounds using the first integrals of the linear centers.
Oh, okay, nice.
And these upper bounds, in case, for instance, of the parabola n equals 2 are reached, but we don't know, probably in n larger than 2, probably our upper bounds are higher than the real reached upper bounds, but there exist at least upper bounds for all n at this moment.
Okay, nice. Oh, it would be nice to compare these upper bounds with this.
I will send you the paper.
Yeah, it would be, eventually we reach it.
Jaume, I think that the work of Douglas, the table 2, is the perturbation of the centers in the with the averaging. This or is in the center case?
In my case, are center and center fixed.
No.
Arbitrary linear centers.
Okay, it's not center case. It's focus case actually.
Okay. Then
it's perturbing.
Table 2 is for linear in general. Linear. What we are discussing now, Jaume, I think is linear.
Yes. In my case, is linear. Yes.
Well, then I stopped the recording because I think it's enough for today.
Yes.